Alright, in this video we're going to look at a infinite series here, and we're going to use the integral test to determine whether this converges or diverges. And so what we need to do is we need to find a function that will agree with this seed sequence here for all the positive integers. That function that we find needs to be continuous on 1 to infinity and needs to be positive. So if we just swap out the n's with x's, this will be our function that we want to use here. And if we replace, so we're going to have f of n is equal to a n for all n. So that's going to meet the requirement for the integral test in that respect. And the next thing we need to do is we need to show that this sequence is decreasing. So if we can show that the function is decreasing, then we'll have that condition met for the integral test. And how we can show a function is decreasing is to use the first derivative and show that the first derivative is negative. In this case, for the integral test, needs to be from 1 to infinity. So we'll go ahead and take the derivative. It's just the quotient rule. So it's going to be low d high minus high and then d low all over low squared. Okay, and then we'll go ahead and simplify that down. So 2x squared plus 10x plus 12 minus 4x squared minus 20x minus 25 all over the common denominator squared. And we'll go ahead and clean up the numerators. So the 2x squared minus 4x squared will make a minus 2x squared. 10x and minus 20x will make a negative 10x, and 12 and minus 25 will make a negative 13. So what we can do here is we can factor out the negative, and so that'd be negative 2x squared plus 10x plus 13 all over the denominator squared. And this is going to be negative on 1 to infinity, no problem. The denominator is always positive, and the numerator is always going to be negative on 1 to infinity. And that's all we need for the integral test. Oops, I said 0 to infinity. It's true there also, but for the integral test we'll need it for 1. So then what we're going to do is we're going to compare this with the integral here. So 1 to infinity, improper integral. 2x plus 5 over x squared plus 5x plus 6 dx. Okay, so this is rigged to be a nice u substitution problem. So u will be the denominator, and du will be the numerator. And so what we're looking at, if we just look at it in terms of just the integral, that's 1 over u du. And so that's going to be natural log absolute value of u plus the constant of integration. And because we have the this is an improper integral, we'll go ahead and introduce the limit when we write it up here. So we're going to go ahead and so this is equal to the limit as b goes to infinity, ln absolute value of x squared plus 5x plus 6 evaluated from 1 to b. And that's the limit as b goes to infinity. We'll go ahead and evaluate it at b and evaluate it at 1, and then we'll go ahead and take the limit of that. So this is going to go to infinity. If I subtract 12 from it, not even 12, if I subtract natural log 12, I'm not going to affect it, so it's going to be infinity. Okay, and because our indefinite integral is infinity, that means that the integral diverges, that improper integral diverges. Now what the integral test said is the sum and the integral either both converge or diverge. Now since the integral diverges, that tells us that the summation or that infinite series is going to diverge by our integral test. Okay. And so again, we just had to run through to make sure the conditions for the integral test were met. Our function is continuous. The function agrees with the sequence for all n. Positive, continuous function, and then we need decreasing as well. That was part of the conditions for the integral test. Okay, and so we have one that diverges by the integral test.